Welcome to The Explainer. Ever wondered how your computer can find one specific file in a sea of thousands, like instantly? Today we're going to pull back the curtain on the secret behind that speed. We're talking about one of the most elegant and powerful algorithms out there, binary search. It's truly the art of the smart search. To really get a feel for just how clever this is, we're going to start with a problem that sounds simple on the surface, but can turn into a real headache if you don't approach it the right way. Okay, so picture this. You've got this long 48-minute recording. Your job is to find the single precise moment someone grabs a water bottle. Seriously, how would you even begin? Well, the most obvious way, the one we'd all probably think of first, is also, well, it's the most time-consuming. Let's call it the slow search. Yep, this is the brute force method. You just hit play and watch, second by painful second, just scanning the screen until you finally spot it. In the world of computer science, this has a name. It's called a linear search. And for our 48-minute video, that could literally mean a 48-minute wait. There has to be a smarter way, right? Oh, you bet there is. It's a brilliantly simple strategy known as divide and conquer, and it completely changes the game. So, how does this much cleverer approach actually work? Let's break it down. Instead of starting at the beginning, you do something radical. You jump straight to the middle, the 24-minute mark. Then you ask one simple yes or no question. Has the bottle been picked up yet? If the answer is no, what does that tell you? It tells you the event must be in the second half. And just like that, bam, you've eliminated 24 minutes of footage in a single step. And from there, you just do it again. You take the remaining half, jump to its middle, ask the question, and keep slicing your search area in half. With each jump, you're closing in on the answer at an incredible speed. I mean, the difference in efficiency is just staggering. But, and this is a really big but, there's one crucial catch. For this smart search to work, your data has to be sorted. A linear search can plow through a jumbled mess, no problem. A binary search absolutely requires order. For our video, time itself provides that order, right? Everything happens chronologically. Okay, so now let's see how this divide and conquer idea gets turned into the formal algorithm that computer scientists know and love as binary search. So we're going to trade our video timeline for a sorted list of numbers, what programmers would call an array. But the core idea is exactly the same. We start off with 2 pointers. We'll call them L for left, parked at the very beginning of the array, and R for right, sitting at the very end. Our entire search is going to happen between these 2 pointers. First things first, find the middle. So the middle indexed between 0 and 5 is 2. We take a look at the value at that position, and we see it's the number 5. And now we ask our key question. Is our target number 10 bigger or smaller than this middle value, 5? This simple comparison is what lets us throw away half the data. Well, 10 is obviously greater than 5. And since we know for a fact that our list is sorted, there is no way, 0 chance, that our number is in that first section, so we can just get rid of it entirely. So to shrink our search space, all we do is move our left pointer up to the spot right after the middle. And just like that, we're ready to do the whole process again, but on a much, much smaller list. So we do it again. The new middle between index 3 and 5 is index 4. We look at the value there and boom, it's 10. A perfect match. We found it in just 2 steps. A linear search would have taken 5 steps. Now you might think, 2 versus 5, what's the big deal? But this is where the magic scales. If our list had 1,000,000 items, a linear search could take 1,000,000 steps. Binary search, it would find it in about 20. 20 steps. That is mind-blowingly efficient. That's the power of what's called logarithmic time complexity. But there is a hidden danger lurking in this beautiful algorithm, a really subtle bug that even very experienced programmers can fall for. Yeah, this is a real gotcha. What happens when your list has, say, billions of items, and the index numbers themselves are pushing the absolute limits of what a computer's memory can hold? Well, you can run into something called integer overflow. The easiest way to picture it is like an old car odometer. When it hits 999,999 and you drive 1 more mile, it doesn't become 80,000,000. It rolls over to all zeros. Integer overflow is kind of like that, but often, instead of 0, the number wraps around and becomes a huge negative number, which, as you can imagine, completely breaks our search.
And here is where that sneaky bug lives. Look at these two formulas. On a piece of paper, they're the exact same thing, mathematically. But for a computer, that first one is a ticking time bomb. If L and R are both gigantic numbers, adding them together first could be the thing that pushes the sum over the limit and causes that overflow. The safe formula, though, is much smarter. It calculates the distance between the points first, which is a smaller number, cuts that in half, and then adds it to the starting point. It gets the same answer, but completely avoids the risk.
It's such a tiny change, but it's the difference between code that works and code that could fail spectacularly under pressure. It's a perfect example of how, in programming, the devil is always, always in the details. You see, binary search is way more than just code. It's a powerful way of thinking. So here's a final thought for you. From figuring out why your Wi-Fi's down to organizing a massive project, where else could you apply this divide and conquer strategy to find solutions faster? Once you start looking for it, you'll realize it's absolutely everywhere.